All right, so let's review Taylor's series and the Maclaurin series. So those two very, very important series, and we use every day. And the calculator, we use all the time, but it's just hiding behind the buttons. So the definition of Taylor's series is this. So if f has derivatives of all orders at x equals a. So I don't know if you have ever learned the term called smooth. Smooth. I'm going to type in the chat. Okay. So the function is smooth. So which means so when the function has derivatives of all orders, you can take a first derivative, second derivative, third derivative, it keeps going on. So we call smooth functions. So if f is a smooth function, then the Taylor series for the function f at a is this, all right? It's the summation. Remember before we have cn multiplied by x minus a raised by n, right? Now we already proved, right? The proof is in the textbook. The cn can be represented as this. It's closest, so cn is just related with its derivative of nth order, but divided by n factorial. Because when we take derivatives, right? When we take derivatives, there's factorial involved because of permutation. Take a first order. Imagine second order. Second order, we have taken the terms twice if it's not zero, right? Twice. So on and so forth. That's why we need divided by n factorial. So just the nth, so cn is the derivative of the function, nth order of the function, is the nth order derivative of the function divided by n factorial. Because when we take an nth order derivative, the specific term being permuted. So a in this case will have x minus a raised by n. A is called the center of convergence. Because when x equals a, this series always converges, right? This is equal to the function value f of a. All the rest of the terms become 0, right? So it always convergent, at its center. So we can expand. When we expand, we get f of a, the function value at a, the first derivative at a multiplied by x minus a, linear, right? Linear term. At prime of a, we know exactly that's the rate of change, right? And then multiplied by x minus a, plus second order of the function evaluated at a at the center, divided by 2 factorial, then x minus a squared, quadratic terms. So we call this part linear approximation, linear Taylor's approximation. And the 3 terms, function value, first order, second order, we call quadratic approximation. And so on and so forth. And the Maclaurin series is just a special Taylor series because a equals to 0. Right? So in general, we just call Taylor series. But when the center is 0, we call Maclaurin series. Let me know if anyone has any questions. So Taylor series is unique, right? And if a function can be represented with a Taylor series, it's unique. Of course, same thing for Maclaurin series, right? Because Maclaurin series is a special case of Taylor's series or Taylor polynomial. So f has n derivative at x equals a. Then the nth Taylor polynomial for f at a is just take the derivative up to n order. Yeah, up to order of n. So her function value, first order multiplied by the linear x minus a, second order divided by 2 factorial multiplied by x minus a raised by square, third order divided by 3 factorial x minus a to the third power, so on and so forth to the n derivative divided by n factorial multiplied by x minus a raised by n. Okay, so this is called nth Taylor polynomial. I think for this book, and then the homework is just to do linear approximations, so linear or first order Taylor polynomial, or second order or quadratic Taylor polynomial. So that means just go the first 3 terms. Linear, first 2 terms. Quadratic, first 3 terms, or second order, so on and so forth. Same thing for Maclaurin. Maclaurin just means a equals 0. We just have x. So this example we have done already. So let's not do. We have done all those. Yeah, Taylor series with a remainder, right? Sometimes when the function, you know, non-increasing means either decrease or, you know, stay like a constant. And the tail, the remainder, we call Rn. So just imagine we have this nth polynomial, nth order derivative. Okay, so this is nth Taylor polynomial. So nth Taylor polynomial. We have Taylor derivative up to nth order. And what about the rest? The rest we just call, because the series is an infinite series, they have infinite many terms. So we could just call the remainder everyone like n plus 1's order derivative divided by n plus 1 factorial times x minus a raised by n plus 1, so on and so forth. Right? There's still infinite many terms. And because for certain functions, especially for convergent functions, that remainder will go to 0 as n goes to infinity. So we just call it Rn. So Rn. And a convergent series, Rn will go to 0. So let's see Taylor's. So Taylor's theorem with remainder. Well, f of x equals to Rn of x plus Pn of x, right? Pn means nth polynomial, nth Taylor polynomial, right? We have n plus 1 terms. Function value plus the first order, second order derivative up to nth order derivative. So the remainder equals to the function f of x minus the nth order Taylor polynomial. So, right, so Rn of x, right, is this. It's a summation. I don't know why this missing summation. So Rn should be the summation of the rest of the terms. I think this is a typo here. So this line has a typo, okay. Rn is a summation of all the n plus 1 powers. N plus 1, n plus 2, n plus 3, so on and so forth. All the rest of the terms. Okay, maybe this one just, I don't know why this only has one term. Oh, okay. All right. So this is just has a condition, extra condition. So Taylor's theorem with the remainder says the function f itself can be differentiated n plus 1 times. So we don't even consider the rest of the terms. So this is for this theorem. So the function can be differentiated n plus 1 times on the interval containing the real number a. So let Pn be n's Taylor polynomial of f at a, and so then of course this is true, right? Because we're only consider up to n plus 1 term. So Rn then will be the n plus 1 term. That's it. And right, if the derivative n plus 1 order derivative is bounded by a number, it has upper bound, then the tail Rn is bound. Right? This actually doesn't, for us, it's not so important, but for the math major, it's important. So this one, we have, let's just review this again, because I'm sure this will be on your test, will be on your final. So this is saying use linear and quadratic approximations to estimate. That's what our calculator do exactly, right? If we key in cubic root of 10, the calculator would put into Taylor's Maclaurin series or Taylor series to calculate, right? To give us approximation. It depends on how the calculator is set up. So under each button is a function. The function is represented as a either Taylor series or Maclaurin series. It depends on how people program the calculator. Okay. So let's see this example. This example is saying f of x equals the cubic root of x. So what do we want to do? We want to find the first and second Taylor polynomials for f at x equals a. Okay, at x equals a. So this x equals a means the a equals a. The a is the center. The center equals 8. And use okay, we don't want to do that. So use this to polynomial estimate. Then use it to estimate cubic root of 11. Let's see that. So when you take derivatives of this function, right? So first derivative will be 1 over 3x raised by 2/3 power. Then we evaluate at the center, right? F of a function value at a is 2. The first derivative at a is 1 over 12. Second derivative at a is negative 1 over 144, so on and so forth. But we are only care about finding the first order approximation, a second order approximation. So we only need to have first order derivative and second order derivative. Then we put into the Taylor series definition. So first order Taylor polynomial, or is it just first order approximation, or the linear approximation. It's just this. It's just the function value at the center plus first derivative at the center multiplied by x minus 8. Right? And then we'll simplify, we'll plug in the value, which is equal to 2 plus 1 over 12 x minus 8. It's a linear function. Similarly for P2, so we have a function value at a, we have first derivative of a of times x minus a linear term. Then the second order f double prime of a divided by 2 factorial times x minus a squared. Okay, we have 3 terms here. So, after we simplify a little bit, we get a quadratic function. So first order Taylor polynomial is a linear function. Second order Taylor's polynomial is just quadratic approximation. Now we can use these two functions, linear function and quadratic function, to approximate cubic root of 11. Right? Using linear one, we will get 2.25. Use quadratic one, get 2.21875. Okay. We can do more. We can do more. If we do more, if we take more terms, if we do higher order Taylor polynomial, the value, the approximation will be more precise. So to calculate R1 or R2, we use Taylor's theorem with remainders, right? Right, same thing. So this one, this part, actually we just don't care much. Okay, anyone has any questions for this? So this is important. A and B are important for us, for non-math majored. So we have to be able to use at least linear approximation or quadratic approximations. Linear approximation represents first order Taylor polynomial. Quadratic approximation represents second order Taylor polynomial. All right. So linear approximation is a linear function. Quadratic approximation is a quadratic function. All right, so let's keep going. Let's see this example. Approximating sine x. Right? Sine x is just a trig function. And we can use Maclaurin polynomial to represent sine x. And of course, we can do for e to the x power, we can do cosine x. And I think before we calculated it, right? So we got x minus x cubed divided by 3 factorial plus x divided by 5 divided by 5 factorial, so on and so forth. And then this one, for this one, only goes to 2n plus 1 order. So using the fifth Maclaurin polynomial for sine x to approximate sine pi over 18 and bound the error. Okay, for us, we don't care much about the bound error. B, for what values of x does the fifth Maclaurin polynomial approximate sine x to within 0. Okay, for the second one, we have to use Rn. So this is the fifth. So we have to use R6 to bound. Well, let's see the example. So fifth Maclaurin polynomial, right? Remember the center is just 0. So we don't have x minus 8. We just have x. Because x minus 0 is just x. So Maclaurin series centered at 0. The center is 0. So P5 of x is equals x minus x cubed divided by 3 factorial plus x raised by 5 divided by 5 factorial. You may ask, well, we're going to fifth, right? Aren't we supposed to have 6 terms? Yes, we're supposed to have 6 terms, but the other 3 are zeros. Because when we take a sine, right? The other 3 are zeros, so it disappeared. And using this polynomial, we can estimate sine pi over 18. Or sine pi over 18 just equals to this function plug in pi over 18. So we get function, we get the x value pi over 18 minus 1 over 3 factorial times pi over 18 raised by 3 plus 1 over 5 factorial multiplied by pi over 18 raised by 5. Right, so this we put into calculator. So for this we put into calculator, we approximate, that's about 0.17 something. So again, that's exactly what our calculators do. So when we key in sine of pi over 18, provided the calculator is set for radian metric, then the calculator will return to us 0.173648. It may have more digits, for more advanced calculator. It may has less digits for even simpler calculator. Anyone has any questions? No question is stupid. What's the significance of this if you're going to plug into the calculator anyway? That's a great question. Okay, so yeah, I remember I asked this class, right? It seems like none is mathematics measured. If you are measuring mathematics, especially if you're measuring pure mathematics do not approximate anything. Pure mathematics want everything to be exact, you know. But the more, you know, for life, we use more about applied math because we want to apply math models in life. But with pure mathematics, we want everything to be exact, like square root 2, right? We don't want to approximate with 1 point something. And we want to keep it as square root of 2. But for applied mathematics, we have to get a value so we can apply to life. So how do we calculate? Let's see well, sine of pi over 18 is not so obvious, but think about the cubic root. No, not square root, cubic root. Let's even think about the square root of 2. So how do we, you know, understand or use square root 2 in life? So we have to approximate. So how do we approximate? Is exactly going through Taylor's series or Maclaurin's series. Does that answer your question, Ali? Yes, right. We plug into calculator anyway, but now we know why, right? Since we know this now, so we know how the calculator works. You know, why we punch into square root 2, it comes back 1.41 something. It's because of this, because of Taylor, because of, you know, behind each button, it's been programmed. Taylor's series or Maclaurin's series. More like Taylor's series, because Maclaurin series is centered at 0. Right? Let's see, square root of 5, right? Or square root of 4.1. We want the center to be 4. We don't want the center to be 0, because 4.1 is far away from 0. Okay, any other questions? Same thing for sine of pi over 18. We remember sine pi over 6 is half, right? For some of the signs, we have beautiful values. We have 0, half, 1, -1. Then we have some rational values, square root 3 over 2, square root 2 over 2, so on and so forth. So to approximate sine pi over 18, you know, we can do exactly the same thing. We can do Taylor's series, Taylor's polynomial to approximate. Okay. So so let me talk about this. This may not be put in the final exam, but maybe it's good to know. So the remainder, remember, is just R6 because we're taking 5th order, right? So R6 of pi over 18, just the 6th term, the 7th term, right? The 7th term, because the first term is a function value. So the first term is always a function value. Then for second term is the first order, so on and so forth. So we can calculate that. And then we can put this in, since we're looking for less than or equal to 1 for all x, we just calculate, right? But this is not so important for us. Let's see this one. Use the fourth Maclaurin polynomial for cosine x to approximate cosine pi over 12. Remember, let's all try this. Remember cosine x, the formula? Comparing to, so this is for sine x, right? It's x minus x cubed divided by 3 factorial. Cosine x is 1. Well, let me not, let me be exact. Cosine x, I think this is 6.2. Or maybe it's 6.3. Oh, it is 6.3. No, it's not. Oh, maybe in the first one. Remember we did a calculation for, oh, right here, e to the x, sine x, cosine x, right? Let's see cosine x. So for cosine x, in the end, we do the calculation. Let's see. Let's see this one. So to the fifth order, so we get a 1 minus x squared divided by 2 factorial plus x raised by 4 divided by 4 factorial. It seems like it just mixed up for sine x. Right? Sine x is x minus x cubed divided by 3 factorial plus x raised by 5 divided by 5 factorial, so on and so forth. So for cosine, it is 1 minus x squared divided by 2 factorial. Let me write down this. So you may want to write down this too. 1 minus x squared divided by 2 factorial. Plus x raised by 4 divided by 4 factorial. Right? P2, or P1 is equals 1. P2 equals 1 minus x squared divided by 2 factorial. The first two terms. And P3 is the same as P2 because third power derivative is 0. And P4 equals P5 equals 1 minus x squared divided by 2 factorial plus x raised by 4 divided by 4 factorial. Now let's go to our practice. Oh, we didn't do this. Maybe we should do this too. You know what? Let me just finish. Maybe so. If when we have time later, so I'll give you time to practice those two. 6.12. So let me write down 6.12, 6.14, I guess. No, 6.13. If we have time, we'll come back here. So we also talk about representing a function, especially a rational function, with the Taylor series or with Maclaurin series. And if we do that, we can determine the interval of convergence. So this one function is 1 over x. We'll take the derivative up to fourth order. Then we evaluate at the center given. Center is 1. So we want to determine the interval of convergence because each one time when we approximate, we get a function. So we take the derivatives, right? We evaluate at the center 1, we get all this. And then we see we can write the nth order derivative of the function as f of nth order takes 1 as input. That equals -1 raised by n factorial. So that's, concluded from the pattern. So for center at 1, the function can be written by this. -1 raised by n, x minus 1 raised by n goes from 0 up to infinity. To find the interval of convergence, we use the limit ratio test, right? We compare n plus 1 term with n's term. So hopefully some canceled, then we're left with a function of x minus 1. So usually we put absolute value signs around it because we want that one, because according to the limit ratio test, right? The absolute value of the ratio needs to be less than 1 for the series to converge. Otherwise, it just diverges. So in this case, we see absolute value of x minus 1. That means x can be as small as 0 or as big as 2. Right? So we solve the absolute value inequality. We get x is in between 0 and 2. That's the interval. Open parenthesis 0, comma 2, close parenthesis. Right? At the center 2, we can plug into x as 2. So we could calculate, right? Summation sign of -1 raised by n, 2 minus 1 raised by n, actually equals to, from 0 to infinity, -1 raised by n. So this is the isolate. This is the isolate series. Okay. And the diverges, so it converges in this, right? The interval of convergence is 0 to 2. And it converges to what? It converges to that. Diverges by the divergence test. Similarly, at x equals 0, and the 0 is x minus 1 is -1 raised by n. Then -1 raised by n times -1 raised by n, that's -1 raised by 2n, n plus n 2n. Then -1 raised by 2, that become +1. +1 raised by n, just forever n, right? So the interval of convergence is just open parenthesis 0, comma 2, close parenthesis. Okay, anyone has any questions for this? Original function is 1 over x. Okay, so checkpoint 6.14. Well, let's come back for this. Yeah, last time we even talked about this a little bit, right? So 1 over x can be written as 1 over 1 minus x. Why we want to do this? Because we want to write in the form of a geometric series, right? Geometric series requires the ratio to be, absolute value of the ratio to be less than 1. So basically, the boundary in between -1 and 1. Can I be smaller than -1? Can I be bigger than +1? Okay. In that case, the geometric series converges. Okay, convergence of Taylor series. So suppose f has derivatives of all order on the interval containing a, then containing the center. A is the center, right? Then the Taylor series converges to f for all x in the interval if and only if limit of Rn of x goes to 0. Okay, that means up to certain terms, up to n's terms, the rest of the terms are very, very close to 0, or may become 0 already. So So it converges, you know, when the remainder is 0. Okay, so R with full node n means the n plus 1 term. Is the n plus 1 term. Let's see an example. So this one we want to find the Maclaurin series. Maclaurin series is centered at 0. Okay, that's the only difference from Taylor series. For each of the following, find Maclaurin series and its interval of convergence. And use Taylor's theorem with remainder to prove the Maclaurin series converges to F. So which means we want to show Rn, the limit of Rn when n goes to approach to infinity, Rn goes to 0. Okay. So the first one is e to the x, the second one is sine x. All right. So e to the x, sine x, cosine x are famous. Okay, we need to memorize them. We need to memorize. Oh, actually, you know what? None of you math majored. If you're math major, you have to memorize them. Okay, let's see the example. Let's see first one, e to the x. Right. If we remember, e to the x has a representation of x raised by n divided by n factorial, and n goes from 0 to infinity. Imagine the first term, right? The first term just 1, because x raised by 0 is 1, and 0 factorial is 1. So 1 divided by 1 is 1. So for e to the x, first term is 1, and plus x squared divided by 2 factorial, plus x cubed divided by 3 factorial, so on and so forth. All plus, not alternating. Excuse me. So we want to, we want to find out the interval of convergence. We do the same thing. We use the ratio test. So we compare the absolute value of the n plus 1's term with n's term. Okay. So then we simplify. We're left with absolute value of x divided by n plus 1. Because the first term we have x raised by n plus 1. The denominator has x raised by n. So then, of course, x raised by n, divided by x raised by n, that's 1. I'm left with absolute value of x only. Then n factorial divided by n plus 1 factorial. That just, becomes 1 over n plus 1, right? Because n plus 1 factorial can be written as n plus 1 times n factorial. Then n factorial divides itself, becomes 1. Now we plug into the limit. So limit of the ratio just equals the limit of absolute value of x divided by n plus 1, right, as n approaches infinity. And we see clearly the limit goes to 0, right? Absolute value of x, we can just pull out of the limit. Then we consider the limit of n approaches infinity, 1 over n plus 1. Well, 1 in the numerator is constant. The denominator keeps growing bigger to infinity, right? 1 apple shared by all people on earth. So everybody gets almost nothing, right? So that's what limit. So that's that's an analogy of limit of this when n approaches infinity goes to 0. So therefore, the series converges absolutely for all x. And thus, the interval of convergence is negative infinity up to positive infinity. Okay. So the interval of convergence is all real numbers. All real numbers. So show the series converges with each x for all x. We use the fact that n's order still equals e to the x, right? For all n greater than or equal to 0, for all n be non-negative. So the e to the x is an increasing function, right? Because e is 2.71a something. So the base, so e to the x is exponential function. When the base is greater than 1, it is exponential growth, right? So it's increasing function. So the maximum value of e to the x for all absolute value of x less than equal to b is e to the b, right? So now we can put these bounds for the remainder. So Rn of x is just n plus 1's term in the series. We simplify a little bit, so we get the absolute value of x raised by n divided by n factorial. That's from the top, right? We just showed from here. Converges for all x, but the divergence test we know, so we conclude, right? If we do choose e to the x so we get this, e to the x converges at all real numbers because the n plus 1's term goes to 0. Okay, anyone has any questions? We see very similar to Taylor's series, right? Because Maclaurin series is just centered at the origin. This is a equals 0, that's it. It's like a... How do we get to the Rn line? How do we get to the Rn line? You mean this one? Let me highlight. This one? That's the definition. That's the definition. So Rn equals to, what's Rn? Rn equals to the derivative, the nth order derivative, evaluate at the given point, divided by n plus 1 factorial, multiplied by x minus a, but this here center is 0, so just x raised by n plus 1. Right? And here, we have e to the b, because we know absolute value of x is bounded by b. So where does this come from? Maybe that's your question, right? Why the maximum value of e to the x for all absolute value of less than or equal to b is e to the b? Because the function is just e to the b, right? Okay, all right. Yeah, so this line just with the equal sign. So Rn is equals to Fn's order of x divided by n plus 1, right? Factorial. And because we know absolute value of x is bounded by b, so e to the x is bounded by e to the b, right? So that's why we have this less than sign also, because it's bounded above, it's maximum. So this way we just showed this, right? This series converges for all real value of x. And by divergence test, we know that the limit of n plus 1's term when n approaches infinity goes to 0 for all real numbers x. So combining those two facts, the result is the limit of the remainder as n become large enough, so that equals to 0. Okay, so this happens for all convergent series. The second one, using the nth Maclaurin polynomial centered at 0, right? Again, for sine x. And we find that Maclaurin series for the x is given by this. Negative 1 raised by n, x raised by 2n plus 1 divided by 2n plus 1 factorial. Right. Remember, so here n goes from 1 up to infinity. So, we apply ratio test. Once we apply ratio test, we simplify, get this. Get absolute value of x squared divided by 2n plus 3 times 2n plus 2. So now let's take a limit of this when n approaches infinity. And indeed, absolute value of x has nothing to do with n, so we can pull out of the limit sign. So we just take a limit of n approaching infinity 1 over the factors involve n in it. Well, that has to be 0, right? It has to be 0 because the numerator is fixed. The denominator is a function of n. As n grows bigger, the denominator grows bigger. So this remainder goes to 0. So that proves the series converges for all real numbers. Any other questions? Okay, let's keep moving. Okay, that's for today. I think we can spend a couple minutes to try the work. Let's try 6.15 first. So, this is cosine x. Use ratio test to show that interval of convergence is all real numbers. Show that the Maclaurin series converges to cosine x for all real numbers of x. Okay, let's all try 6.15. Then we're going back to try 6.14, 13, and 12. Then we talk more about working with Taylor's series. Okay, let's all try 6.15. Remember cosine x minus, let me type in the chat actually. Cosine x cosine x is just, so nth term, right? Nth term, the numerator is x raised by 2n divided by n factorial, like Lorentz series, right? Why I put a parenthesis? I don't need parenthesis. Oh, I need parenthesis for this power. And of course, n goes from 0 up to infinity. Oh, I forgot a -1 because it's an alternating series. So -1. The denominator is 2n. Oh, you're right. The denominator, right. Okay, I'm totally wrong. Let me rewrite it. So it's -1 raised by 2n. I better put the parentheses around. -1 raised by 2n. What negative x? Let me be lazy. Negative x raised by 2n, because it starts with 1. So the first term is 1. Then divided by 2n factorial. So you first find the derivatives of each term up to a certain point, then evaluate the pattern to find the series. Okay, Damon, let me understand you. So are you talking about to find the series for cosine x? Your question is about to find. Oh, okay. That one we did before. Let actually, it'll be good for us to review a little bit because this is a long break, right? We did a calculation. Let's just review. 6.2 or 6.3? Oh, here. Okay. Let's just review. Sine x, cosine x are very similar. Let's do C. Let's do cosine x. Okay, first, even before this, the definition is very important. Let's go back for the definition. You see, this definition is for nth Taylor polynomial, right? Even before nth power, let's see the series definition for series. Okay, so let's go back here. We have to remember what's Taylor series, what's Maclaurin series. So everything started from here. So remember, in the very beginning, we have a Cn multiplied by x minus a raised by n. Maybe let's even go back. Oh, right here. So in the beginning, we said, okay, now infinite series or power series, right? So a power series can be represented like this way. So that's just definition. So Cn multiplied by x minus a raised by n. The first term will be C naught, then plus C1 times x minus a plus C2, x minus a squared, so on and so forth. So this is the definition for power series, right? It's a polynomial, but it's an infinite polynomial because, we know polynomial functions very well, right? But a polynomial functions has a leading term. Which means, nth power of a polynomial, which means the leading term is nth power. Let's say quadratic function. Quadratic function, who's the leading term? The leading term is x squared term, right? The term with x squared in it. And the linear function, who's the leading term? The leading term is the one with x, right? So that's called a polynomial function. But this one is very similar to polynomial function, but it's not a polynomial function. Why? Because this one has infinite many terms. There's no leading term. So that's the difference. So a power series we can understand as, very similar to polynomial functions, but it has infinite many terms. So how do we represent? We represent this way. Cn multiplied by x minus a raised by n. N goes from 0 up to infinity. And to educate our brain or register this idea, we can write out some terms. The first term will be C naught, because when n equals 0, right? When n equals 0, we get C naught multiplied by x minus a raised by 0, which is 1, right? We get the first term. Second term, we get C1 multiplied by x minus a raised by 1, so on and so forth. So that's the definition of a power series. Now, in the power series family, the two special series. One is called the Taylor series, one is called the Maclaurin series. Maclaurin series is a special case of Taylor series. You see, this is center. We call this A, the center of the power series. So when the center is not 0, we will call Taylor series. When the A equals 0, we call Maclaurin series. Okay, coming from power series family, now let's talk about Taylor's. So here we did a calculation to say, okay, Cn is closely related with the derivatives. You see, if we take a first derivative, first order of derivative, what do we get? What do we get? At A, at the center, we just get C1, right? Because the rest of the terms, we get A minus A goes to 0. Similarly, let's see C2. So this is the first order derivative. So when we take a derivative of this power series, first order, we just get C1. Second order, we get a 2C2. Third order, we get 3 times 2 times C3. Well, we could see this is 2 factorial, 3 factorial, right? And so on and so forth. So this is telling us the Cn is closely related with the derivative of the function. And what do we do? Because we have this factorial as coefficient, so we need to offset with that. We'll offset with that with a divide by n factorial. So Cn, so come from power series. Now we observed the relationship of each Cn, or each coefficient of the x term. It's just related with its derivative, with its order, same order of derivative. So now we can write the power series in this way, right? So Cn becomes this. Of course, here we're talking about the functions, right? And so we got a definition for Taylor series. So Taylor series, so we need a function has all order of derivatives, a smooth function, at a certain point. So the Taylor series is defined this way. Nth order of derivative divided by n factorial, evaluate at the center of A, multiplied by x minus A raised by n. Of course, we can write out a couple of terms, So when n equals 0, we just get the function value at the A. When n equals 1, get these first order derivatives, evaluated at A, multiplied by x minus A, so on and so forth. And the Maclaurin series just means that A equals 0. So now come back to a question. So now we want to do cosine x, right? So let's do cosine x again. So cosine x, so our function is cosine x. We need to find the first order derivative, second order derivative, third order derivative, then evaluate at the center. Right here. Okay, so now let's do cosine x. So cosine x centered at 0, right? So x equals 0. Basically, actually this will be Maclaurin series, right? Because centered at 0. So function equals cosine x, first derivative is negative sine x, evaluate at 0. Function value will be 1. First derivative at 0 will be 0. Second derivative will be negative cosine x, evaluate at 0, we get negative 1. Third order derivative sine x, evaluate at 0, get 0. Fourth order, get cosine x back to the original function. So first order, evaluate at 0, get 1, back to 1. Right? Periodic function. So now we see all those zeros. Right? Zeros accuse so many terms. Now let's plug into the definition of Taylor's series. Right? If we take only the first term, that's just 1. Second term, we have 1 plus 0, right? So 1 plus 0 times x minus x. 0 times x, that's 0. So take 3 terms, we have 1 function value plus 1 plus the second one, which is 0. Then, because this is alternating, right? Because we get negative, positive, we could see the derivative, f raised by 2m. So the 2m, the order of derivative at 0 is negative 1 raised by m. So observe this pattern. So second order at 0, second order derivative at 0 will be, second order will be m equals 1, right? So m equals 1, we get we get second order. Second order, evaluate at 0, get negative 1 raised by 1, which is negative 1, which is this one, which is the middle one. And you can do more. You can see, okay, if we do 2m plus 1, let m be 0, 2 plus 1, which will be third order derivative, evaluate at 0, third order is 0. Right? You may try fourth. Right? So then we plug into, so we get this, in general, we have negative 1 raised by m for the order of 2m derivative. Then we plug into the Taylor's series definition. So we get this, right? So this we calculated up to fifth order of derivative. Function value is this, first order is this, second order, third order and second order the same, fourth order and the fifth order the same, because the zeros, right? Because of zeros here. Because this is this is periodic. We can imagine the fifth order evaluated at 0 will be 0. Sixth order evaluated at 0 will be negative 1, so on and so forth. So we get 1 minus x squared divided by 2 factorial plus x raised by 4 divided by 4 factorial, then minus x raised by 6 divided by 6 factorial, then plus x raised by 8 divided by 8 factorial. Okay, Damon, does that help you a little bit? Okay. Try to calculate yourself at least once, right? At least once. By using the definition, by calculating the derivatives of cosine, and evaluate at 0. You don't really have to evaluate at 0. You could evaluate, choose any center, choose pi over 2 or choose pi. Then plug back into the Taylor series definition. Okay, But this one, we're not doing Taylor's polynomials, right? This one, we want to find Maclaurin series for the function cosine x, right? Cosine x. Let me do in the chat. Maybe we go to the whiteboard. So use the ratio test to show the interval of convergence is this, is all real numbers. And show that Maclaurin series converges to cosine x for all real numbers of x. All right, this one is very similar to actually the book that did sine x. Let's just go back to sine x, because cosine x and sine x are very, very similar. So let's get back to B, sine x. So sine x, the nth term has a Taylor polynomial for, let's see, this one is Maclaurin series representation, right? Summation sine, n goes from 0 up to infinity, -1 raised by n, x raised by 2n plus 1 divided by 2n plus 1 factorial. That's the nth term. That's the nth term of sine x representation in Taylor series, in Maclaurin series, because the center of this one is 0. Because we don't see x minus a, parentheses raised by 2n plus 1. We see x itself, that means x minus 0. So the center is at 0. Right? This one is above cosine x. So if you want to review, go back to the previous one, in the same section 6.3. So we have the textbook calculated e to the x, sine x, and cosine x. So here we just use that. We just use that saying sine x, equals to this Maclaurin series, right? And the nth term is represented as -1 raised by n, x raised by 2n plus 1 divided by 2n plus 1 factorial. Now, we want to find the interval of convergence for this series, right? For sine x that being represented in this Taylor series or Maclaurin series. So we use limit ratio test. Okay? We use the limit ratio test. Remember, limit ratio test is the absolute value of n plus 1 term divided by nth term. So n plus 1 term here is just absolute value of x raised by 2 of n plus 1, right? 2 of n plus 1, because n plus 1 term now, then plus 1. Well, 2 times n is 2n, 2 times 1 is 2, 2 plus 1 is 3. So that's how we get 2n plus 3 here. So this is the n plus 1 term. And then also have 2 parentheses n plus 1 plus 1, right? That's 2n plus 2 plus 1, which is 2n plus 3 factorial. So this is the n plus 1 term in the series, right? Then divided by nth term, or multiplied by the inverse of the nth term. So the nth term is just, x raised by 2n plus 1 divided by 2n plus 1 factorial. So the inverse, we just flip 2n plus 1 factorial in the numerator, and x raised by 2n plus 1 in the denominator. Then we put the absolute sign all around. But n is positive, right? N is non-negative because n starts from 0. So we can, we can put the absolute value sign around x only, because only x contribute to negative or positive. Then we simplify, we get absolute value of x squared divided by 2n plus 3 times 2n plus 2. Now we take a limit of this, right? We take a limit of this, absolute value of x squared has nothing to do with n. So we can pull out absolute value of x squared outside the limit. So what is the limit when n approaches infinity? 1 over 2n plus 3 times 2n plus 1. That's obviously 0, right? Because the numerator 1 is constant, and the denominator n goes to infinity. So that limit just goes to 0. All right, remember limit ratio test says if the limit is less than 1, remember that. So limit of this equals 0 for all x. And this is just x, right? We don't have x minus something or x plus something. So this says, so when the limit of this equals 0, that is to say the interval of convergence is just all real numbers, right? Because it doesn't matter what x value is. The limit of 1 over 2n plus 3 times 2n plus 2 goes to 0. So the conclusion is the convergence, so any x number, any number works for x. Any real number works for x. So that's why the interval of convergence is all real numbers. Does that make sense here? Anyone has any questions? All right, okay. Yeah, if you have any questions here, if I'm confusing you, please stop me, all right? Then, okay. Yeah. So similar way, we can prove this. We can just mimic for sine x. All right, so today we're going to 6.4. Working with Taylor series. Okay, so basically we want to use Taylor's, we want to put the Taylor series into use. So we want to write terms of the binomial series. Recognize the Taylor series expansions of common functions. Recognize and apply techniques to find the Taylor series for a function. Use Taylor series to solve differential equations. Use Taylor series to evaluate non-elementary integrals. All right, so we're going to talk, probably we're going to cover a little bit. So there's a famous function. Okay, let me just read this part for you. In the preceding section, we defined the Taylor series and showed how to find the Taylor series for several common functions by explicitly calculating the coefficients of the Taylor's polynomials. Right, remember that? We basically use the Taylor series definition and find the derivative of a given function. Right? Then we just evaluate at the center. So in this section, we show how to use this Taylor series to derive Taylor series for other functions. We then present two common applications of power series. So first, we show how power series can be used to solve differential equations. Second, we show how power series can be used to evaluate integrals. When the antiderivatives of the integrand cannot be expressed in terms of elementary functions. Well, what does it mean, elementary functions? Polynomial functions, rational functions, exponential functions, logarithmic functions, and trigonometry functions. So those 5 types are called elementary functions. In one example, we consider integral e to the negative x squared dx, an integral that arises frequently in probability theory. This is very, very important. And right, later on, if you ever get into multivariable calculus, you will see e raised by negative x squared plus y squared, stuff like that, with two variables anyway. So the first one, the binomial series. Our first goal in this section is to determine the Maclaurin series for the function f of x equals 1 plus x raised by r for all real numbers of r. Okay. Remember the binomial theorem we learned in pre-calculus, right? In pre-calculus course. So we have a plus b raised by n, right? N is required to be whole number. That means n can start with 0, but it goes up to 1, 2, 3. So n has to be whole number. But here we're dealing with 1 plus x raised by r, especially this is 1 plus x raised by r, and r can be any real number. R can be pi, r can be square root 2, right? So that's the fancy part of this. So the Maclaurin series for this function is known as the binomial series. So we begin by considering the simplest case. R is a non-negative integer. So we recall that for r equals 0, 1, 2, 3, 4, it can be written as this. Right? This is just normal binomial theorem. Right? We learned in pre-calculus. 1 plus x raised by 0 equals 1, 1 plus x raised by 1 equals 1 plus x raised by 2. This is called perfect square. So 1 plus 2x plus x squared. 1 plus x raised by 3, perfect cubes. So 1 plus 3x squared plus x cubed. How do we get these coefficients? Something called the Pythagoras, oh my goodness, I couldn't remember. Triangle, not Pythagorean triangle. Okay, anyway. So the expression on the right-hand side are known as binomial expansions, right? So this on the right-hand side called binomial expansions in binomial theorem. And the coefficients are known as binomial coefficients. And those one comes from, so more generally for any non-negative integer r, the binomial coefficient of x raised by n in the binomial expansion of 1 plus x raised by r. So r now is this whole number, is given by out of r things, choose n things, right? Combination. Okay. Combination, right? So this is a formula for combination. Out of all things, we choose n of them, right? If we have 10 apples on the table, you know how many ways I can choose 5 apples randomly? You know, how many ways? That's r factorial divided by n factorial divided by r minus n factorial. So we see the coefficient is just this, just the combination. So the first one, the first term, first coefficient is just, you know, out of r choose nothing. Then out of r choose 1, out of r choose 2, so on and so forth. So for nth term, so we have a representation, we can write as summation sign, and goes from 0 up to r. So out of r things, choose n things, right? X raised by n. For example, using this formula for r equals 5, we get this, right? Out of 5, choose 0. Out of 5, choose 1. Out of 5, choose 2. Out of 5, choose 3. Out of 5, choose 4. Out of 5, choose 5. The first one is always out of n things, choose 0. The last one always from n things, choose n things. Right? That's only one way. Or from n things, choose nothing. There's only one way. So that's why we see the first. We see the coefficient of the first one is always 1, right? 1x cubed, 1x squared, so on and so forth. So for this one, we have 1 plus 5x plus 10x squared plus 10x cubed plus 5x raised by 4 plus x raised by 5. The coefficient we can also get from something called the Pascal's triangle, right? Pascal's triangle, which means We make 1, then 1, 1 keeps going down. We add the ones in the middle. Okay. But now, we want R to be any real number. So the exponent of R becomes any real number now, not necessarily a non-negative integer. If R is not a non-negative integer, then 1 plus x raised by R cannot be written as a finite polynomial. So however, we can find a power series for f. Specifically, we look for the Maclaurin series for f. So to do this, we find the derivatives of f and evaluate them at x equals 0. Okay, so 1 plus x raised by R is a function for us. And we use the definition of Maclaurin series, right? Maclaurin series is just Taylor series centered at 0. So we need to find all levels of derivatives. So what's the derivatives? So function is 1 plus x raised by R, or R is not variable, right? X is a variable, R is just some number. So the first derivative will be R times 1 plus x raised by R minus 1. Second derivative will be R times R minus 1 times 1 plus x raised by R minus 2. So on and so forth, right? Up to nth level, we would have R factor R times R minus 1 times R minus 2, multiplied by 1 plus x raised by R minus n, right? Because we're talking about Maclaurin series, right? So let's evaluate those at 0, because Maclaurin series is centered at 0. So function value will be 1. First derivative at 0 will be R. Second derivative will be R times R minus 1. Third derivative will be R times R minus 1 times R minus 2. Nth order will be R times R minus 1, R minus 2, multiplied by R minus n plus 1. Right? So now let's put it into Cn. Remember Cn, just nth order derivative divided by n factorial, right? So the nth order evaluated at 0 is R times R minus 1, keeps going down, R minus n plus 1. Then we divide this by n factorial. And what is that? That's just out of R choose n, right? Out of R things choose n things. Because remember that we have R factorial divided by n factorial multiplied by R minus n factorial. What's R factorial divided by R minus n factorial? That's exactly R times R minus 1 times R minus 2, times R minus n plus 1. So this one is to verify why each coefficient just this, right? Just combination of R choosing n things. Anyone has any questions? So with this notation, we can write the binomial series for 1 plus x raised by R as this. Combination out of R choose n things, x raised by n. So get a 1, the first term will be 1, second term will be R times x, and third term will be R times R minus 1 divided by 2 factorial x squared, so on and so forth. So on and so forth. So to determine the interval of convergence for binomial series, okay, so we have talked about Taylor series, Maclaurin series, so this is talking about binomial series. So of course we apply ratio test, right? We apply ratio test, we simplify, in the end we get R minus n absolute value, and R minus n times x divided by n plus 1, always absolute value in it. So we take a limit, let n goes to infinity. What do we get? We take a limit of this one, right? We can pull x outside. We see actually that equals to absolute value of x. Hold on 1 second. So the ratio, we get r minus n divided by n plus 1. Why do we get x less than 1? Oh, okay. So when we take a limit, right, when n goes to infinity, what's the limit of this? R minus n divided by n plus 1. Well, absolute value of r minus n can be written as absolute value of n minus r, right? So in the numerator, we have n. In the denominator, we have n divided by n, that's 1. So the ratio regarding n is just 1. So 1 multiplied by absolute value of x, right? So absolute value of x less than 1 if only if absolute value of x less than 1, right? Because if this is less than 1, we conclude the interval of convergence is -1 to 1. Anyone has any questions? This basically is a review of ratio test. We use ratio test to determine, if a series converges or not. If the limit of ratio is less than 1, it's convergent. The series is convergent. So the behavior at the endpoints depends on R. So it can be shown for R, greater than or equal to 0, the series converges at both endpoints. For R, greater than -1, but less than 0, the series converges at x equals 1. And it diverges at x equals -1. So you can just plug in x equals 1 and x equals -1. Right? And for R less than -1, the series diverges at both endpoints. So the binomial series does converge to 1 plus x raised by r in the interval of -1 to 1 without the n 2 points for all real numbers r. But proving this fact by showing that the remainder Rn of x goes to 0 is difficult. So that's why. So here we use a limit ratio. We use a ratio test. We use a ratio test to determine, where and the interval of its convergency. Anyone has any questions? Okay, let's keep going. So let's see this definition. For any real number r, the Maclaurin series for 1 plus x raised by r. Remember, r is a real number. That means r can be rational or irrational. Is a binomial series. It converges to f for absolute value of x less than 1, right? We just showed. Right? And we write 1 plus x raised by r equals to summation sign. The coefficient of x raised by n is just out of r things, choose n. If we read out a couple of terms, we get this. And of course, for absolute value of x less than 1, because the convergency, because the representation only to be valid in the interval of -1 to 1. Out of the interval, the representation, the equal sign does not exist. Anyone has any questions? Now, let's put this in use. So let's see an example. So we want to find binomial series for function square root of 1 plus x, so a, right? Then we want to use this to estimate square root of 1.5. By the way, the calculator, when you punch into, is exactly doing such process. But it depends on the function. You know, if we approximate 1.5, probably it's just this function, square root of 1 plus x. If we want to approximate the square root of 2.5, it might be 2 plus x, so on and so forth. Okay, let's see this example. So in this case, what's r? R equals the half, right? R equals the half, a rational number. So we just use the binomial series, right? Usually we get 1 plus half x plus half times negative half divided by 2 factorial x squared plus half times negative half times negative 1 minus half, which is negative 3 halves, divided by 3 factorial, then x cubed, so on and so forth, right? That's from the definition. That's from this definition. Okay. So we simplify, well, we calculate or simplify, in the end we get this. We get a 1 plus summation sine n goes from 1. 1 goes from 1 up to infinity, negative 1 raised by n plus 1 divided by n factorial. Because we have alternating series, right? Negative 1 raised by certain power is involved. Then we see the pattern is 1 times 3 times 5 times da 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 da. Nth term is 2n minus 3. Then divided by 2 raised by n. Okay, so this is just nth term. And n goes from 1 up to infinity. So a third order, which just takes the first three things, right? First three terms, 1 half x, and it's up to square. So 1/8 x cubed, right? So we plug in, we get 1 plus half x minus 1/8 of x squared plus 1 over 16 x cubed, because we only want to do third order, right? We only want to do third order. So if we want to use this to approximate the square root of 1.5, right, we have 1 plus 0.5 raised by half. We plug into this approximation. We get 1 plus half times half minus 1/8 times half squared plus 1 over 16 times half raised by cube. We use calculator to approximate, that's about 1.2266. Okay, anyone has any questions? So that's how we use in life. Common functions expressed by Taylor series. So 1 over 1 minus x is just x raised by n, and the interval of convergence is from negative 1 to 1. E to the x is x raised by n divided by n factorial. Well, n also goes from 0 up to infinity, and x can be any real number. Sine x is a little bit difficult to remember, but remember the exponent is odd, and the denominator is odd number factorial. So odd number, we use 2n plus 1 to represent. Because the 2n, it forces the number to be even. Then plus 1, it forces the number to be odd. Right? And the interval of convergence is all real numbers. If you think about it, sine x is periodic. Same thing for cosine x. right? Cosine x, we have this representation because cosine x is x raised by an even power divided by an even factorial, even number factorial. To force a number to be even, just multiply by 2. So 2n, the 2 doubles n all the time. So it forces the exponent of x to be even number. And 2n forces the denominator to be an even number factorial. And cosine x is not too far from sine x. Remember cofunctions. So the real number is also all the interval of convergence is also all real numbers. Okay. ln of 1 plus x. We didn't really do this. If you want to have fun, you could do this. You could check out this yourself. So function ln of 1 plus x has a representation of summation sine n goes from 1 up to infinity, -1 raised by n plus 1, x raised by n divided by n factorial. Then x goes from -1 up to 1, including 1, but not -1. Arctangent x can be represented as -1 raised by n, x raised by 2n plus 1, divided by 2n plus 1. Looks very similar to sine, right? What's the difference? Sine, the denominator is 2n plus 1 factorial. But for arctangent, it's only 2n plus 1, no factorial. Okay, that's the difference. And the interval of convergence for sine x is all real numbers. But the interval convergence for arctangent is going from -1 to 1. Okay, lastly, 1 plus x raised by r. So we have this out of all things choose n to combination to be the substitute, the n's power of derivative divided by n factorial, x raised by n. Also, interval of convergence is from -1 to 1. I would encourage you, all right, so this is important. I would encourage you to calculate each one's Maclaurin series, all right, for at least 5 terms. For at least 5, at least 5 terms, Then to verify, right? So you use Taylor's series definition to write out its series representation. Then to compare with this, right? Compare with Maclaurin series. And also pay enough attention to calculate each interval of convergence, right? If you do a couple of times, if you do a couple of times by hand, and you will see the logic behind it, and you will memorize it too. So your brain will register and try to memorize them. Okay, let's see if we have time for this one. So this is cosine square root of x. So what's annoying? Annoying is the square root of x. Right? So instead of x, we have square root of x. Square root of x. Right? So we just use, the cosine x expansion, but change x to be square root of x. But because here we have square root of x raised by 2n, the 2 saved the square root of x to be x. So we don't have x raised by 2n, which is for cosine x before. Now it becomes x raised by n divided by 2n factorial. So I think in your homework, I'll assign you some homework similar to this. You use the existing Taylor series or Maclaurin series to write a function, very close to it. Sanch, so when I go into Sanch, Sine is just this way. Okay, we'll leave this one for next class. So anyone has any questions? Because we had a long break, so if it's confusing, go back, starting from 6.1, all right, to review a little bit. And I will assign you some homework to practice on, how to use Taylor series and how to, and also Maclaurin series. Okay, I guess that's it for today. And if you have questions, you may stay. If you don't have questions, have a good night. See you on Thursday.